So in this video we're going to go over doubling time and half-life for exponential functions. And the exponential functions we're going to write in this form, p0 times e to the rt, where r of course is the relative rate of change and p0 is just the initial value. And the doubling time and half-life we're going to denote by td and th. Okay, d for doubling and h for half, obviously. All right. So what is the doubling time? Doubling time is just how long you have to wait until you have double of what you started. And the half-life, similarly, is just going to be how long you have to wait until you have half of what you started. So in the case of doubling time, your r is going to be positive because it has to grow, it has to double. And in the case of half-life, your r has to be negative because your thing has to decay. Okay, you have to wait until you get half of it. So the goal, or at least the first goal in this video, will just be to get formulas for the doubling time and the half-life. All right, so we want formulas for the doubling time and the half-life, and the formulas are actually going to be pretty simple to remember, in fact, and that's going to come from the fact that we're using exponential functions. That's actually the reason why we're using them. So p of td. So let's take td and plug it into the exponential function. Okay? And by definition of doubling time, when you plug it into the exponential function, you should have double of what you started with. Got it? But now, since you plugged something into the exponential function, you know that you're going to get p0 times e to the r td, right? Because that's what it means to plug it into the exponential function. That's still equal to 2 times p0. And look what you can do. You can cancel out p0 by dividing by p0 on both sides. You want to solve for td, so to do that, you want to get that down, right? So it's in the exponent, you want to get it down, so you take ln of both sides, and you get ln e to the rtd equals ln of 2. Of course, the exponent comes down, that's just the log rule, and you get times ln e. Don't actually have to write that because we all know that ln e is equal to 1. So we could just ignore that. That's still equal to ln 2. And so writing it up here, we have td, dividing both sides by r now, is equal to ln of 2 divided by the rate r, which is in purple. Okay, so that is the formula for doubling time. And notice one interesting thing here, that it doesn't depend on p0. See, because we canceled it out in the beginning. Doubling time does not matter. It doesn't matter what the initial value was. So actually the doubling time is something that holds for whatever time you start at. All right, and that has something that's intimately related to the fact that for exponential functions, the relative rate of change is a constant. It's just the number r. Okay, anyway, you'll see more of that later. But let's get the formula for half-life. That's th. Okay, what is that going to be equal to? Well, you run through these same steps. Okay, you jump through these same hoops, except you're going to replace d with h, and you're going to replace the number 2 with the number 1/2, because you want half of what you started with, right? And so you should get ln of 1/2 divided by still the relative rate of change r. And that's the formula for half-life. Again, the thing to point out here is that it doesn't depend on the initial value. Okay, so let's do some examples. First one, so you have some bacteria colony growing. Okay, so it's growing. Here you go. The rate it grows at is 5% per second. Then the colony is going to double every, well, how often? So obviously this is a doubling time problem, but you're going to have to make the assumption that the bacteria is growing continuously. That's why we can use exponential functions. Okay, so that's why we can use our formula for TD. It's just going to be what? ln 2 divided by the rate. Well, r in this case is 5% per second, so it's divided by 0.05. And if you plug that into your calculator, you're going to get 13.8629 seconds. There you go. So let's say you start out with one bacteria. Then 13.86 seconds later, it's going to split into 2. 13.86 seconds later, it's going to split into 4, etc., etc. Okay, that's how doubling time works. let's do one more example, but this time for half-life. So let's say you have some element, it's decaying at the same rate, let's say, just to make things simple, and you want to know how long until half of that radioactive material is gone. All right. So again, we're going to assume that we can use exponential functions, and in this case, again, it's reasonable. Radioactive materials decay exponentially. And we're just going to use our formula for half-life, which is TH equals ln of a half divided by R. But what is the R in this case? Well, we know that this thing is decaying. Okay, I'll erase that later. So we know that this thing is decaying at a rate of 5% per second. So R is actually negative 0.05, and we want half of it to go away. So we're of course going to use the half-life formula. And let's just wait for the computer to do some thinking here. It's working really hard in the background, and I don't know why. Cut that out, and TH is equal to ln of a half divided by negative 0.05. And if you plug that into your calculator, you'll see that you actually get the same answer as before. All right, 13.8629 seconds. And actually, that's not a coincidence. Okay, the reason, well, I mean, we chose the rate to be the same, and so really, what is this saying? What are these two examples saying? If the relative rate of change or relative growth rate is the same as the relative decay rate, then the doubling time will be the same as the half-life. Okay, and that's, I mean, might seem obvious to say it, but actually it depends simply on this mathematical fact here that ln of a half, okay, is equal to ln1 minus ln2, but ln1 is 0, so you have negative ln2. Because this is a decay rate in the case of half-life, when you divide negative ln2 by negative 0.05, then those negatives cancel out and you get a positive, and that's why it's the same answer as before. Alright, so anyway, it wasn't a coincidence, and it had to do with the fact that the relative rate of change is a constant. Alright? Okay, for exponential functions. So that's all we're going to do in this video, and you'll see more of doubling time and half-life in other examples in subsequent videos.